Good morning, everyone. Today is lecture number 34 of this heat treatment class, and today we're gonna solve a numerical that is basically related to carburizing only. And you people know carburizing is a diffusion process where the carbon atoms are diffusing onto the surface of the steel, right? Which makes the steel surface more harder and more wear resistance, right? Which basically we want. But how to know what is the time, like how much time we have to do carburizing so that we can get a particular concentration of carbon at a particular depth of the steel, right? Because suppose you want 2 depth, suppose you want 3 depth, and the carbon concentration is suppose some definite weight percentage, right? So how much time you have to expose the steel to the carburizing atmosphere? So that is the question we have. So the question is, we have a plain carbon steel with carbon of 0.25 weight percentage, and it is subjected to carburizing heat treatment. Right? The temperature of carburizing is given 1000 degrees centigrade, and at a depth of 1.5 the carbon concentration should be increased to 0.5 weight percentage. Right? So what is given, and also it is given at surface of the steel the carbon concentration is maintained at 1.2 weight percentage of carbon. Basically it is a gas carburizing. You can understand, suppose it is a gaseous atmosphere and the concentration of gaseous atmosphere at the surface of the steel is 1.2 weight percentage of carbon, and this will be remain fixed throughout the carburizing process. So find out the time required to increase the carbon percentage to how much? 0.5 weight percentage of carbon at a depth of 1.5 mm, right? So these are the given things. Okay, let me write over here. The initial concentration initial concentration okay. So initial concentration, that is, we can write C0 is equal to 0.25 weight percentage of carbon, right? So it is given. And what is also given? Temperature.
Sir, can you listen, sir?
It is not visible.
Yes, sir.
Okay, let's want to keep your ring annotation. Keep. Okay. Now it is visible.
Yes, sir.
Okay. So initial concentration of carbon in the steel is given, that is 0.25 weight percentage of carbon, and it is also given temperature of carburizing. Temperature of carburizing. Sorry. So I am finding difficulty in writing actually. It's not so easy work actually. Okay. Here, okay. So Okay, let me use paint otherwise. Okay. So now, yes, temperature. Okay. And so temperature is given 1000 degrees centigrade, right? So this is the carburizing temperature, right? Then what else is given? Surface concentration is also given here. Surface concentration of carbon at the surface of the steel, that is 1.2 weight percentage, right? Okay. It is visible to everyone?
Yes, sir.
Yes, sir.
The writings are clear? Actually, I am finding some difficulty in writing here. This is the first
Sir,
time
you
I am
can
using.
type in notepad also.
Yeah, I can type it, but the problem is I have to show some figure, and it will be not so easy to draw the figures. Okay, anyway, so the surface concentration is 1.2, which will remain fixed throughout the carburizing process, as I told. What else is given? Yes, depth is given. So depth. So what I can write? Depth from surface is given, that is 1.5 mm, right? So up to this depth, we have to increase the carbon concentration up to how much? 0.58%. So at this depth, the carbon concentration is, so what I can write? Carbon concentration at this depth will be equal to how much? It will be 0.5, 0.5 These things are given. You can see initial concentration of the carbon is given 0.25. Temperature of carburizing is given 1000 degrees centigrade. Surface concentration of carbon, that means the carburizing atmosphere, concentration of carbon is 1.2, which will remain fixed throughout the carburizing. And yes, it is actually how much? Into then yes, it is 0.5. So percentage and carbon concentration at this stage is okay. Okay, depth. Okay, depth from the surface is it is how much? 1.5. Should it? 1.5 mm. So at this depth, 1.5 mm depth, we want uh, we want how much carbon? 0.58%. So this is double actually. You can see this 0.25 and this is 0.5. So question is the time t. Sorry. So we need to find out the t. So how much time will be required to get this much weight percentage of carbon 0.5 at a depth of 1.5 mm, right? So this is the question. So how to solve this? So okay, what else is given? Obviously d naught is given. So diffusion data are given. Diffusion data. Diffusion data are given. Diffusion data. What is the diffusion data? So it is given d naught is equal to, this is your frequency factor, that is 2.3 into 10 to the power minus 5 meter square second inverse. So this is also given. This is 2.3. d naught is equal to 2.3 into 10 to the minus 5 meter square second inverse. And activation energy is also given. Activation energy for diffusion. It is given 148 kilojoule per mole inverse. Okay. This is given also. Equation energy, you understand. Okay. So these things are given. So how to approach this kind of problem? So we have to first find out a definite expression. By using that expression, we can do the exercise and we can solve the numerical. Fine. So before moving into that, let me draw a plot to explain the process. Suppose this is your specimen, and suppose let you are exposing this surface to the carburizing atmosphere. Just imagine the situation. This surface you are exposing to the carburizing atmosphere, and the surface concentration is given already, as I told you, 0.258% of carbon, and here at the surface the concentration of carbon is how much?
Sir, you are not clearly audible, sir.
I'm
There
not
is
clearly
problem
audible.
in your mic.
Hello.
Now it is clear, sir.
Am I audible to everybody else?
Yes, sir.
Yes, okay, fine.
But
So,
sir, so much noise is there.
okay, so much noise is there. Okay, anyways, so this is, you understand, this is a mild steel. The surface concentration is given 0.25, and here the atmosphere concentration is given already, right? Uh, that is 1.2 weight percentage of carbon, right? So now if you draw a profile like this, suppose uh, I want to actually draw a profile of concentration, carbon concentration. So this is the thing. Suppose this is your distance x, and this is the uh, suppose weight percentage of carbon. Fine. And this is, for example, this is your C0, initial concentration of carbon at the surface or inside the material. Same. That is already you know how much. That is 0.25 weight percentage. Fine. Weight percentage. Fine. And concentration, suppose this is the surface concentration of carbon. The concentration of carbon which is maintained throughout the carburizing process, that is CS, surface concentration. Already you know that that is 1.2 weight percentage of carbon, right? So this is the surface concentration 1.2, and this is the concentration at in the steel, carbon concentration in the steel, right? So at T is equal to 0, concentration of carbon on the steel surface is everywhere, that is 0.25. Okay, fine. But at T, carbon diffuses into the material and we get a profile. Huh. And we want to find out the time T, where at a depth of 1.5 mm, the carbon concentration will be 0.58%. So if I want to draw a profile, fine. And as I told, this is the, actually, why this is this profile. So suppose this is your depth, that is 1.5 mm. This is the carbon concentration, and this is your this time T. The concentration is this much. How much? This is 0.5. Right? So at a depth of 1.5 mm, we want to find out how much time it will be required to get the carbon weight percentage of this one, 0.5 weight percentage of carbon. So this is Cx, comma T. I'll explain why this is Cxt.
Sir, MD is requesting to join the meeting.
Sorry.
Mohammed is requesting to join this meeting.
Okay. So the best way to write a concentration profile uh, is in terms of C. Okay. Fine here. C X comma T. So this is the best way to write the concentration profile, right? That is the concentration as a concentration. Here the concentration of carbon as a function of distance x at a time interval t. So there is a general expression for that. I'm writing here the general expression for the concentration at a distance x at a time t, that is C x t is equal to a constant A plus a constant b, that is error function of x, that is the depth, divided by 2 square root of dt. So this is the general expression. I think you might have gone through this kind of expression in the diffusion problems in transport phenomenon, maybe. I'm not sure about that. Have you people gone through this kind of expression earlier?
Yes, sir.
Yes,
Phase
sir.
transformation.
In the phase transformation? Okay, very good. Then we might have a good idea about that. Have you solved this kind of numerical earlier?
Yes, sir.
Yes, sir.
Okay, you have solved this one. Anyways, we'll solve it again. No problem. So, so that means you understand. We have to find out this A. What is the value of A, and what is the value of B, so that we can easily solve this numerical. And you understand this is the depth, as I told, which is already given, and this is the time period, and this is the diffusivity. So now we have two things. First thing is we have boundary conditions. Boundary condition we have, and we have what other thing? We have initial condition also, because we have initial carbon concentration is known. Initial condition. So we have two things. One is boundary condition we have, and we have initial condition. Right? So for boundary condition, I can write C as a function of 0 and T. That is equal to already I have written, that is CS, right? Concentration at the surface, which is kept maintained constant, which will be not changing throughout the carburizing process. And for initial condition, the time is 0, obviously, so I can write C concentration is a function of x and time period 0, because this is the initial condition. There is no diffusion at all. It is equal to C0. Right? So here time is 0. And concentration will be equal to C0. Right? This is CS. Now, this is, as I told, this is our main expression to solve the numerical. So I want to put the boundary condition first into this expression. This error function expression, I want to put this boundary condition problem. Boundary condition thing into this one. Right? So how I can write? I can write. You can see here. Here, x is 0, right? Am I audible to everyone? Right? Am I audible to everyone?
Yes, sir.
Okay, you can see here x is 0, right? So if I'll put here 0, so what I will get? That means error function of 0 is 0. You have to remember, I am writing otherwise. ERF, error function of 0 will be also 0. You have to remember this one. This is important. Because why? Error function of x, because x is 0 here already. It is present over here, right? So I can write directly now C 0 t, C as a function of 0 t, this one is equal to CS is equal to A. It is okay? You would have understood now why it is A? Yes or no?
Yes, sir.
because this is 0, error function of 0 is 0, and this will become 0, this term becomes 0. So finally we will left with this A. Fine. Then if I want to put the initial condition now, initial condition, which is C as a function of x times 0 is equal to C0 in this error function equation. So what I can write? So you can see here t is 0, right? So this will be 0, right? So this expression will be 0. So x by 0 means infinity, and error, you have to remember, now I can get error function of infinity is equal to 1. You have to remember. This is again important. You have to remember. So error function of 0 is equal to 0. Error function of infinity is equal to 1. You have to remember. Right? So the expression will become C x 0. C as a function of x distance and time 0 is equal to C0, which is already there. That will be equal to, then this part will become A plus B. It is fine now. It is okay.
Yes, sir.
So now we got CS. So this is important actually. CS is equal to A, C0 is equal to A plus B. So CS is the surface concentration and C0 is the initial concentration on the surface of the steel, right? So also we can write, so I can write now B is equal to, if you compare these two equation, I can write what? Okay, I can write C0 equal to, okay, let me erase this one, otherwise. Okay, now I can write as A is equal to CS, so I can write C0 is equal to CS plus B. Yes or no? Or I can write B equal to C0 minus CS. It is okay? And now I can, so we can, that is CS is equal to A, or A is equal to CS, and B is equal to C0 minus CS. Is it okay? Okay, next, move to next slide. Now suppose now you want to substitute the A and B. We got A is what? We got A is equal to CS as A, okay, A equal to CS, and B we got, that is C0 minus CS, already we got, and we can substitute the A and B, this A and B we can substitute in the error function expression. So we will get a good expression to solve the numerical, that is C as a function of x distance, and that is depth, and time t is equal to CS plus C0 minus CS error function of depth x to square root of dt. Okay, so we got a very good expression, and we can use this expression to solve our numerical. Right? So now this is the thing, we can rewrite this expression. This expression can be rewrite like, I can write error function x 2 root dt is equal to c x t minus cs divided by c0 minus cs. We can rewrite this above expression like this. Again, this is interesting. So this equation will be helpful to solve the numerical. So in the examination, you can directly use this expression to solve this. Do not have to derive all these things. If you remember, you just remember this expression. C error function of x by 2 square root of dt is equal to cxt minus cs by c0 minus cs. Where you remember, this is the surface concentration, this is the C0 is the initial concentration, and this is the concentration at depth d, at depth x. Right. So at a depth of 1.5 mm, we want a carbon concentration of 0.58%. So we can substitute 0.5 instead of cxt. Okay, finally you can solve it. Error function of x by 2 square root of dt is equal to, instead of cxt, what I can write 0.5, because we want 0.58% of carbon should be there at a depth of x. That is 1.2. CS is already given, and this is 0.25 minus 1.2. Right. So move to the next slide. So I can write, okay, I can write error function of x 2 square root dt is equal to 0.7368. So if you solve that, if you solve this one, okay, if you solve this one, we'll get this value. 0.7368, right? And if you know x, and we can get d from given data of the activation energy and frequency factor. Already the frequency factor d naught is given. We have to find out the d. You can easily find out that soon. Now we have a, okay, I have to give you error function table to solve this. Actually, without the error function table, you cannot solve it. Right now I don't have that, but anyways, if you look into the error function table, okay, let me share it. Otherwise, if I have error function table, okay, this one. So done. I have shared the error function table. You can have a look at that in your WhatsApp. So you can see we have error function of x by 2 square root dt is equal to 0.7368. We got this one. So now for we have to find out, actually we have to obtain that for error function to be equal to this one, error function to be equal to this one, this value, what should be the this one, x by 2 square root of dt actually. So we can write this one, x by 2 square root of dt is equal to z, because in the error function table you have z values And you can see we have z values and we have error function of z values. So error function of z values is this one. So what should be the this z? We have to find out that actually. If you got the z value, we can solve this easily. We can find out the t at the end. So in other words, I can write error function of z is equal to 0.7368. We have to find out this z. We can put this is equal to z, and you can find out the t finally at the end. So from the table, we have to find out this one z. This is 0.7368. Now, if you carefully look into the error function table, we can see we have z values and we have error function of z values. Right? So, if you carefully look, you'll at the end you'll get a value z1 and z2. I can write, which is 0.75, and this one is 0.80, and corresponding error function this one is 0.7112, and this one is 0.7421. Okay, you people have got these two figures from the error function table. Just have a look. Because why we are interested in this two? Because this value 0.7368 lie in between this. Because this is 0.7112 and this is 0.7421. So obviously in between these two we have this 0.7368 value. So we have z1 z2 this one, and we have error function value this one, right? Now okay, you can solve this one like this. You have any other class after this one? You have any class after this class?
Yes, sir. Metal characterization.
Okay, at what time?
11:30.
Okay, fine. I have few minutes. Okay, let me try to solve this. So we have see. So you understand the situation here. Z is given, error function of z is given, right? We have to find out this one for what value of z we have an error function of this one, right? So and this one is lying in between these two values, z1 z2 and error function of z and this one. So how to find this? We have to draw actually we have to draw a plot. Okay, where the x-axis will be z and y-axis will be error function
Sir,
of
sir, depth is 1.5 mm or 0.5 mm?
which one?
Depth x.
What is the x? Already I have told you what is the x. Let's check it. Depth of 1.5
Thank you, sir.
and the carbon concentration should be 0.5. That's double. So you can see error function. Why we are drawing this kind of? Okay, can you remember? Okay, you have already solved this one. Why we are drawing this kind of plot? Error function of z and z. How many of you remember? Because you have to find out the intermediate value in between these two values, right? So this is actually I have to do interpolation. So at z, suppose this is z1. So corresponding error function of z is given. I am writing ERF1 otherwise. So for z1, I have error function of ERF1, right? Similarly, at z2, I have an error function of, suppose I am writing ERF2. It is okay? I can join this 2. Suppose I am writing this A and I am writing this B. So I have to find out Z actually, which lies in between these two. It is okay up to this? You people are getting my point? we have to find out Z, this one.
Yes, sir. Yes.
Okay, so I can project this one here and project this one here. Suppose this is your ERF, error function Z. So what is the Z value when the error function, at this Z value I have an error function of Z value over here, this one, right? So here you can see slope of the line. This AB is a line. So what is the slope? Slope I can write that is n for this AB line, right? So I can find how to find out the slope of this kind of line by, if you remember, okay, ERF, error function of 2, first y-axis, error function of 2 minus error function of 1 divided by Z2 minus Z1, right? So this will your M. It is okay up to this? Error function of ERF2 minus ERF1 divided by Z2 minus Z1 will give you the slope of this line. It is okay? Or I can, okay, I can write again here. Okay, sorry. Or I can write slope M is equal to, you can check. Also I can write this, sorry, I can write this minus this divided by this minus this, same I'll obtain. So slope M is equal to, I can write okay, Z minus error function of 1 divided by Z minus Z1. It is okay up to this?
Yes, sir.
So finally, if you solve this thing, this one, okay, this one is equal to M and that one is also equal to M, right, slope. So I can write error function Z is equal to error function 1 plus M Z minus Z1, right? Or I can write simply Z is equal to Z1 plus 1 by M error function of Z minus error function of Z, error function of Z minus error function of 1. It is okay up to this? Then finally we have to find out M. That's why we are doing these things. So I can write M, that is slope, is equal to, I can put the values directly, 7.421 minus 0.7112 divided by, okay, how much that was actually? 0.80, okay, 0.80 0.80 minus 0.75 is equal to, I will get M is equal to 0.618. I can write finally Z is equal to 0.75 plus 1 by 0.618 into 0.7368 minus 0.7112, right? So finally, okay, this will become, so you will get Z is equal to, from that you will get Z is equal to 0.79. So 0.79. And now we understand Z is equal to x by 2 square root of dt. Right? So I can write simply 0.79 is equal to x. Okay, 0.79 is equal to 1.5. Already it is given, and we have to multiply with 10 to the minus 3. You understand why?
सर डिट्टी ऊपर रूट ओवर दो
Sorry.
सर x divided by 2 root over of dt
2 tau dt it is getting, okay, 0.79. This is 1.5 into 10 to the minus 3, because you have to change the unit, that's why. Then 2 square root of dt. So up to this we got this one. Fine. Final aim is to find out the t. Okay. So and already this is not given actually, d. We have to find out the expression. D is equal to, we understand, d naught exponential function of minus q by rt from the diffusion equation. You understand, d is equal to d naught exponential function minus q by q is, this one is the activation energy area, r is the gas constant, t is the time, right? And d naught already it is given, p exponential factor, or it is frequency factor already it is given. So
The T stands for temperature, na?
yes. This T, capital T is always temperature, small t is the time. Remember that. So I can solve this one. D is equal to, finally I will get 2.3. D naught is given into 10 to the power minus 5 exponential function of minus 148 into 10 to the power 3. 10 to the power 3, you understand why? Sorry. You have to convert the kilojoule into joule. So this will be divided by gas constant 8.31 into T. T, see, you have to remember this is the temperature, and temperature is given 1000 degrees centigrade. So you have to convert into Kelvin. How much? 1213, right?
73.
1273.
Okay, sorry,
1273
Yes, Kelvin scale is called centigrade scale plus 273. Yes. 1273. Okay, fine. So you will end up with, if you try to solve this one, this is 2.3. You'll get 1.93 into 10 to the power minus 11 meter square per second, or second inverse you can write, or second. So now I can write Z is equal to 0.79, that is equal to how much? 1.5 into 10 to the power minus 3 divided by 2 square root of D. Already we obtained this one, 1.9, this much. It is 1.9 into 10 to the power minus 11 into T. Okay. So from this you can finally calculate. You have to solve this and you will get the T. If you solve this, you will get the T value in second, obviously 46503 seconds. Then you have to convert this one into hour if you want, otherwise that is obviously fine. So if you will get nearly 13 hours. So if you hold your steel at that atmospheric condition for 13 hours, you will get a carbon concentration of 0.5 weight percentage at the depth of that much, which is given. Okay, I'll stop over here and continue the lecture from the next class.